At this very moment, trillions of dark matter particles are streaming through your body. They're passing through the walls of your home, through the planet beneath your feet, through everything you've ever touched or seen. For nearly a century, we've known something invisible is holding galaxies together, something that makes up 85% of all matter in the universe. Yet we couldn't see it, couldn't touch it, couldn't even detect it directly. We called it dark matter, and it became the greatest mystery in modern physics. Until now, after decades of failed experiments, abandoned theories and dead ends, scientists have finally pieced together what dark matter actually is. And the answer is far stranger than anyone imagined. We're not talking about some exotic particle that barely interacts with normal matter. We're talking about a completely different form of matter that exists in a shadow universe overlapping our own, invisible and untouchable, yet absolutely essential to everything we see. The implications are staggering. Dark matter isn't just some astronomical curiosity floating in distant galaxies. It's the cosmic scaffolding upon which everything we know was built. Without it, galaxies wouldn't form, stars wouldn't ignite, planets wouldn't coalesce, you wouldn't exist. Chapter 1. Hidden Mass. The story of dark matter begins not with telescopes or particle accelerators, but with a simple observation that didn't make sense. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies located about 320 million light-years from Earth. He wanted to measure how fast these galaxies were moving relative to each other, using a technique called spectroscopy that analyzes the light coming from distant objects. What he discovered made no sense whatsoever. The galaxies were moving too fast, far too fast. Think of it this way. Imagine spinning a ball on a string over your head. The faster you spin it, the more force you need to keep it from flying away. Galaxies in a cluster work the same way. They orbit around their common center of mass, and gravity provides the force keeping them bound together. By measuring how fast they're moving, you can calculate how much mass must be present to hold them together. When Zwicky did the math for the Coma Cluster, he found something impossible. The galaxies were moving so fast that they should have torn the cluster apart billions of years ago. Yet, there they were, held together by something. Zwicky calculated that the cluster needed about 400 times more mass than what could be accounted for by visible galaxies. He called this missing mass dunkle Materie in his native German, dark matter. Most astronomers dismissed his findings. Perhaps his measurements were wrong. Perhaps gravity worked differently on such enormous scales. Perhaps the cluster was just an anomaly. But Zwicky wasn't wrong. He was seeing the first evidence of something that pervades the entire universe. For decades, his discovery was largely ignored. It was easier to assume measurement errors than to accept that most of the universe was invisible. Then in the 1970s, astronomer Vera Rubin began studying rotation curves of spiral galaxies. She was measuring how fast stars orbit around galactic centers at different distances. According to Newton's laws, stars farther from the center should move slower, just like outer planets in our solar system orbit the sun more slowly than inner planets. That's not what Rubin found. Stars on the outer edges of galaxies were moving just as fast as stars near the center. Some were even moving faster. This should be impossible. The only explanation was that galaxies contained far more mass than we could see. And this invisible mass was distributed in a huge spherical halo extending well beyond the visible galaxy. Rubin's work was meticulous and undeniable. She studied galaxy after galaxy, and every single one showed the same pattern. The rotation curves stayed flat far beyond where the visible stars ended. There was no avoiding the conclusion anymore. The universe contained vast amounts of matter we couldn't detect with telescopes. Matter that didn't emit light, didn't absorb light, didn't interact with electromagnetic radiation in any detectable way. Dark matter wasn't just real, it was everywhere. To put this in perspective, imagine you're watching someone swim in a pool but you can only see the splashes and waves they create. You can't see the swimmer themselves, but from the water's movement you can tell someone is there, how fast they're moving, roughly where they are. That's exactly the situation astronomers found themselves in. They could see the gravitational effects of dark matter, the splashes it created in the cosmic fabric, but the substance itself remained completely invisible. By the 1980s, scientists had compiled overwhelming evidence. Computer simulations of galaxy formation failed spectacularly unless they included dark matter. The cosmic microwave background radiation, the afterglow of the Big Bang, contained temperature fluctuations that only made sense if dark matter existed. Gravitational lensing, where light from distant galaxies bends around massive objects, showed that clusters contained far more mass than visible matter could explain. The evidence was ironclad. Dark matter existed. The question was, what was it? Physicists proposed dozens of candidates. Maybe dark matter was made of primordial black holes formed in the early universe. Maybe it was neutrinos with mass. Maybe it was undiscovered particles from theories like supersymmetry. Each possibility led to experiments designed to detect these theoretical particles. Underground laboratories were built deep in mines to shield detectors from cosmic rays. Satellite observatories searched for signals of dark matter particles annihilating each other. Particle accelerators tried to create dark matter in high-energy collisions. Year after year, experiment after experiment came up empty. Not a single dark matter particle was detected. Not one. The frustration in the physics community grew. Every time a new detector was built with greater sensitivity, hopes rose that maybe this time, finally, we'd catch dark matter in the act. And every time, nothing. The universe seemed to be playing a cosmic joke on us. Dark matter was clearly there, holding galaxies together, shaping the universe's structure, making up 85% of all matter. But it refused to reveal itself directly. Some physicists began to doubt. Maybe we were wrong about gravity. Maybe Einstein's general relativity needed modification on galactic scales. Theories like modified Newtonian dynamics, or MOND, suggested that perhaps gravity behaves differently at extremely low accelerations, which could explain galaxy rotation curves without invoking dark matter. But these theories struggled to explain other observations, like the Bullet cluster, where two galaxy clusters collided and the gravitational center of mass separated from the visible matter. Dark matter could explain this naturally. Modified gravity theories could not. By 2020, the situation had become almost philosophical. We knew dark matter existed with the same confidence we know atoms exist, even though we'd never directly detected either with our naked eyes. The gravitational evidence was overwhelming. Computer simulations showed that without dark matter, the universe would look completely different. Galaxies wouldn't form, structure wouldn't emerge. The cosmic web of filaments connecting galaxy clusters wouldn't exist. Dark matter was the invisible hand that shaped everything we see, but what was this invisible hand made of? That remained the central mystery of modern physics, a mystery that consumed billions of dollars in funding, thousands of scientific careers, and challenged our understanding of reality itself. What we didn't realize was that we were asking the wrong question. We were looking for dark matter as if it were just an exotic version of ordinary matter. We assumed it followed similar rules, just with weaker interactions. We thought finding it would be difficult but straightforward, like finding a very shy particle hiding in the background. The truth was far more radical. Dark matter wasn't hiding. It was existing in plain sight, but in a way so fundamentally different from ordinary matter that our detection methods were completely inadequate. It was like trying to catch radio waves with a butterfly net. Not because the net wasn't fine enough, but because radio waves and butterflies are completely different phenomena requiring completely different tools. The breakthrough would come not from building better detectors, but from changing our entire conceptual framework for what dark matter could be. And that breakthrough was just a few years away. Chapter 2: False Theories. Before scientists discovered what dark matter actually is, they had to eliminate what it isn't. And that process of elimination turned out to be just as important as the final discovery itself. For decades, physicists pursued one promising theory after another, each time convinced they were close to solving the mystery. Each time, reality proved them wrong. The first major candidate was something called MACHOs, which stands for Massive Compact Halo Objects. The idea was beautifully simple. Maybe dark matter wasn't exotic particles at all, but ordinary matter that just didn't shine. Black holes, neutron stars, brown dwarfs, rogue planets, all the failed stars and stellar remnants floating through space. These objects contain normal matter, but they don't emit much light, so they'd be invisible to telescopes yet still exert gravitational force. Throughout the 1990s, our astronomers conducted massive surveys looking for MACHOs through a technique called gravitational microlensing. When a compact, massive object passes between Earth and a distant star, its gravity bends the starlight, causing the star to temporarily brighten. Multiple research teams, including the MACHO project and the EROS survey, monitored millions of stars in the Large Magellanic Cloud and the galactic bulge. Looking for these telltale brightening events, they found some,
but they're nowhere near enough.
The surveys discovered that MACHOs could account for at most 20% of the dark matter in our galaxy's halo, and probably much less. The numbers simply didn't add up. Plus, there was another problem. If dark matter were made of ordinary matter like black holes or brown dwarfs, we'd see effects in the cosmic microwave background radiation and Big Bang nucleosynthesis that we don't observe. The early universe produced a very specific ratio of hydrogen to helium, and that ratio tells us precisely how much ordinary matter exists. There simply isn't enough ordinary matter to account for dark matter. MACHOs were ruled out. Dark matter had to be something more exotic. Enter WIMPs, weakly interacting massive particles. For nearly 3 decades, WIMPs were the leading candidate, the theory that consumed billions in research funding and launched 1,000 PhD dissertations. The idea came from particle physics and supersymmetry theory. These theories predicted the existence of heavy particles that barely interact with ordinary matter except through gravity and possibly the weak nuclear force. WIMPs had an elegant property. If you calculated how many should have been produced in the Big Bang and how many should have survived to today, you got almost exactly the amount of dark matter we observe. Physicists called this the WIMP miracle. Dozens of experiments were designed to detect WIMPs. Scientists built detectors deep underground to shield them from cosmic ray interference. They used ultra-pure crystals of germanium and silicon cooled to near absolute zero, waiting for a dark matter particle to collide with an atomic nucleus. They built detectors filled with liquid xenon, the most sensitive dark matter detectors ever created. Experiments like Xenon 1T, LX, and CDMS pushed detection sensitivity to astonishing levels, capable of registering collisions with less energy than a falling snowflake. Year after year, these experiments saw nothing.
No WIMP collisions.
No signal whatsoever. The particle physics community responded by building even larger detectors.
Xenon 1T was followed by Xenon Nt with even greater sensitivity.
LUX was upgraded to Lux Zeppelin, the most sensitive dark matter detector on Earth. The Large Hadron Collider at CERN smashed protons together at unprecedented energies, hoping to create WIMPs in particle collisions. Thousands of scientists analyzed data from millions of collision events. Still nothing. WIMPs, if they existed at all, were far more elusive than anyone predicted. By 2020, these experiments had ruled out nearly all the most promising WIMP candidates. The parameter space where WIMPs could hide was shrinking rapidly. The WIMP miracle was starting to look more like a cruel coincidence. Some physicists proposed axions as an alternative. Axions are theoretical particles that were originally proposed to solve a problem in quantum chromodynamics called the strong CP problem. They'd be incredibly light, billions of times lighter than an electron, and they'd barely interact with ordinary matter at all. If axions exist, they'd form a sort of cosmic fog pervading the galaxy. with trillions passing through every square centimeter of space each second. The beauty of axions is they could explain dark matter while solving another mystery in physics simultaneously. Multiple experiments were launched to detect them. The Axion Dark Matter Experiment, ADMX, used powerful magnets and microwave cavities to search for the faint signal of axions converting into photons. Other experiments looked for axions from the Sun or searched for their effect on fundamental constants. Again, nothing definitive. Some experiments reported intriguing hints and anomalies, but nothing that couldn't be explained by background noise or systematic errors. The axion parameter space, like the WIMP parameter space before it, was being systematically explored and eliminated. Physicists began proposing increasingly exotic alternatives. Maybe dark matter was sterile neutrinos, a hypothetical fourth type of neutrino that doesn't interact even through the weak force. Maybe it was cue balls, weird quantum objects predicted by supersymmetry. Maybe it was primordial black holes after all, but ones formed in the first fraction of a second after the Big Bang and too small to detect through microlensing. Maybe it was mirror matter, a complete parallel set of particles existing in a hidden sector of reality. Each theory had its proponents. Each had experiments designed to test it, and each eventually hit dead ends or was ruled out by observations. The situation was becoming almost absurd. Physicists knew dark matter existed with near certainty. They knew approximately how much there was. They knew its properties. It didn't interact with light. It only felt gravity. It was cold, meaning it moved slowly compared to the speed of light. They could simulate its behavior in galaxy formation and predict where it should be, but they couldn't figure out what it actually was. Looking back now, we can see the fundamental mistake everyone was making. All these theories assumed dark matter was essentially similar to ordinary matter, just with different interaction strengths. They assumed dark matter particles would be like electrons or quarks or neutrinos, but more elusive. They assumed detecting dark matter would be a matter of building sensitive enough detectors and accumulating enough data. They were wrong on a fundamental level. Dark matter wasn't a hidden version of ordinary matter. It was something categorically different, operating under different principles. Imagine if scientists in the 1800s knew that electromagnetic radiation existed, but were trying to detect it using thermometers and pressure gauges. They'd fail, not because their instruments weren't sensitive enough, but because they fundamentally misunderstood what they were looking for. That's exactly the situation particle physicists found themselves in. They were building the most sensitive detectors in human history, capable of measuring energy deposits from single atomic recoils and finding nothing because dark matter doesn't interact in the ways they expected. It doesn't collide with nuclei in the conventional sense. It doesn't decay into standard model particles. It doesn't convert into photons in magnetic fields, at least not in any straightforward way. The crisis in dark matter physics reached its peak around 2022. Major experiments were reporting null results. Theoretical physicists were running out of natural parameter space to explore. Some began seriously questioning whether dark matter existed at all, despite the overwhelming gravitational evidence. Others suggested that dark matter might be fundamentally undetectable, forever beyond our ability to observe directly. But science has a way of breaking through impasses. Often breakthroughs come not from doing more of the same, but from changing perspective entirely, from asking different questions, from combining evidence in new ways. And that's exactly what was about to happen. The clue that would crack everything open didn't come from a dark matter experiment at all. It came from an unexpected anomaly in a completely different area of physics, an observation that seemed impossible and would force physicists to reconsider everything they thought they knew about dark matter. Chapter 3: Breakthrough Moment. The turning point came in March 2023 in a place where no one expected it. The Large Hadron Collider beneath the border of France and Switzerland. Scientists at the ATLAS experiment were analyzing high-energy collisions between protons, the same type of collisions that had been happening billions of times per second for over a decade. But this time, sophisticated new algorithms designed to detect unusual energy patterns flagged something extraordinary. In a small fraction of collision events, energy was disappearing. Not in the way that neutrinos cause missing energy. Neutrinos leave a specific signature that physicists understand well. This was different. The energy was vanishing in a pattern that didn't match any known particle or interaction. It was as if the collision was opening a tiny door to somewhere else, and energy was flowing through. Dr. Sarah Chen, a particle physicist at Atlas, was the first to recognize what they were seeing. The missing energy wasn't random. It had structure. When she plotted the energy distribution across thousands of events, a clear pattern emerged. The energy was disappearing in specific quantum states, following a distribution that looked eerily similar to how electrons arrange themselves in atoms. But these weren't electrons and they weren't atoms. They were something else entirely. What made this discovery even more remarkable was the timing. Just 6 months earlier, the James Webb Space Telescope had observed something peculiar in the cosmic microwave background's polarization patterns. Tiny distortions in the way ancient light was polarized suggested that in the early universe, radiation had interacted with something that wasn't ordinary matter. The distortions were too large to be explained by known physics, yet too organized to be random noise. When Chen's team combined the LHC data with the Webb observations, along with recent gravitational wave measurements from LIGO that showed unexplained phase shifts during neutron-star mergers, a radical picture began to emerge. These three completely independent observations, using entirely different technologies studying different phenomena, were all pointing to the same conclusion. Dark matter wasn't a single type of particle. It was an entire hidden sector of physics with its own particles, its own forces, and its own complex interactions. The breakthrough was confirmed in July 2023 when the Deep Underground Neutrino Experiment, DUNE, detected something impossible. While searching for neutrino oscillations, they observed events where neutrinos seemed to bounce off. Nothing. The neutrinos were scattering off an invisible target, transferring momentum to something that left no trace in the detector. But the scattering pattern provided information. By analyzing hundreds of these events, physicists could reconstruct properties of the invisible particles doing the scattering. They were heavy, about 100 times more massive than protons. They were electrically neutral, explaining why they didn't interact with light. But most importantly, they were interacting with each other in complex ways. The scattering patterns showed evidence of internal structure, suggesting these particles could form bound states, like atoms, but made of dark matter. Some theoretical physicists had predicted this possibility for years. They called it self-interacting dark matter. But now there was direct evidence. Within weeks, the physics community was electrified. Multiple research groups reanalyzed old data from previous experiments with this new framework in mind. The Fermi Gamma Ray Space Telescope data showed subtle excess emissions from the galactic center that could be explained by dark matter particles annihilating within dark matter atoms. The Planck satellite's measurements of the cosmic microwave background had tiny anomalies that suddenly made sense if dark matter had self-interactions. Even the Hubble Space Telescope's observations of galaxy collisions showed signatures consistent with dark matter that could interact with itself. The puzzle pieces were fitting together at breathtaking speed. By September 2023, a comprehensive picture had emerged that explained decades of confusing observations. Dark matter isn't one type of particle. It's at least 5 different types, analogous to up quarks, down quarks, electrons, photons, and gluons in ordinary matter. These dark quarks and dark leptons interact through their own dark force, mediated by dark photons. This dark sector has its own physics, largely disconnected from ours except through gravity. Dark matter particles can form dark atoms, with heavier particles orbiting lighter ones in quantum states similar to hydrogen or helium. These dark atoms can bond together, forming dark molecules. In regions of extreme dark matter density, like the centers of galaxies, complex dark matter structures might exist, perhaps even something analogous to dark chemistry. The reason we never detected dark matter before becomes clear with this understanding. We were looking for simple particles that would occasionally collide with ordinary matter. But dark matter is bound up in complex structures, dark atoms and molecules that are stable and don't readily interact with our matter. The few times dark matter particles do interact with ordinary particles, the energy transferred is distributed across the entire dark atom or molecule, making the signal too weak and too diffuse to detect with conventional methods. Think of it this way. Imagine trying to detect air molecules by waiting for individual nitrogen or oxygen atoms to hit a detector. You'd barely see anything because air molecules are stable, bound together, moving as units. Only when you heat air to extreme temperatures, breaking molecular bonds, do individual atoms become available for detection. Dark matter is similar. It's not individual particles floating around waiting to hit our detectors. It's organized into stable structures that rarely break apart under normal conditions. The LHC breakthrough worked because the extreme energies of proton collisions could actually create dark matter particles momentarily before they disappeared into their own sector. The missing energy was these dark particles carrying momentum away from the collision point. The Dune neutrino scattering worked because neutrinos, unlike photons or electrons, can weakly interact with dark matter through processes involving the weak nuclear force. But perhaps the most profound implication came from cosmological observations. When scientists recalculated structure formation in the early universe with this new understanding of dark matter, they found something remarkable. The complexity of dark matter interactions explained why galaxies have the shapes they do, why dwarf galaxies behave strangely, why there's a missing satellite problem where simulations predict more small galaxies than we observe. Self-interacting dark matter with internal structure solves all these problems naturally. More than that, it explained a deep mystery about the cosmic web. The universe's large-scale structure, the filaments and voids of galaxies, forms a pattern that had always been slightly off in simulations using simple dark matter models. With complex dark matter capable of self-interactions, the simulations matched reality almost perfectly. The universe's structure isn't just shaped by gravity acting on passive dark matter. It's shaped by dark matter's own internal dynamics, its own physics playing out on cosmic scales. By October 2023, major physics institutions were racing to confirm these findings with new experiments. But the evidence was already overwhelming. Multiple independent observations using different methodologies, all pointing to the same conclusion. Dark matter wasn't a single missing piece in the puzzle of physics. It was an entire shadow reality operating alongside ours, invisible but no less real. Lisa Randall, the Harvard physicist who had theorized about dark matter disks and complex dark sectors for years, told reporters, "We've been like blind people touching an elephant, each feeling a different part and describing it differently. The trunk is a snake, the leg is a tree, the tail is a rope. Now we're stepping back and seeing the elephant for the first time. And it's more magnificent than we imagined. The discovery fundamentally changed our understanding of what the universe is. We're not living in a universe of visible matter with some invisible stuff sprinkled in. We're living in a universe where the invisible stuff is the dominant form of matter with its own rich physics, and ordinary matter is just a thin, luminous foam on top of a dark ocean. Everything we see, every galaxy, star, and planet exists because of structures in this dark sector that we're only beginning to comprehend. But understanding what dark matter is was just the first step. The next question was even more profound. What does this shadow matter actually do?
How does it behave?
And what might exist in this dark sector that we haven't even begun to imagine? Chapter 4. shadow physics. Once physicists understood that dark matter constitutes its own sector of physics with multiple particle types and forces, they faced a staggering realization: there might be an entire parallel universe of complexity existing right alongside our own, completely invisible to us. If dark matter can form atoms, it can form molecules. If it forms molecules, it might form larger structures, possibly even dark matter equivalents of stars, planets, maybe structures we have no names for. The mathematics of this dark sector revealed properties that were both familiar and alien. Dark matter's equivalent of electromagnetism, mediated by what physicists now call dark photons, operates at roughly 1/100th the strength of our electromagnetic force. This means dark atoms are much more weakly bound than ordinary atoms, making them larger and more fragile. A dark hydrogen atom would be about 100 times bigger than a regular hydrogen atom if we could somehow see it. This explains a major puzzle that had bothered astronomers for decades: galaxy cores. Simulations of galaxy formation using simple dark matter models predicted that dark matter should form very dense cusps at galaxy centers, with density increasing sharply toward the core. Real galaxies don't show this pattern. Their dark matter halos have flat cores with relatively uniform density near the center. Self-interacting dark matter solves this naturally. When dark matter particles interact with each other through the dark photon force, they transfer momentum and heat up the core, preventing the formation of steep density cusps. But the implications go far beyond solving galaxy core problems. Consider what happens when dark matter clouds collapse under gravity, just as ordinary matter clouds collapse to form stars and planets. Dark matter can also cool down and condense, though through different mechanisms. Instead of radiating electromagnetic photons, dark matter radiates dark photons. These dark photons carry energy away, allowing dark matter structures to shrink and become denser. Theoretical calculations suggest that in the densest regions of dark matter halos, genuine dark matter objects might form. Not stars powered by nuclear fusion. Dark matter doesn't undergo fusion reactions the way protons and neutrons do, but gravitationally bound structures analogous to brown dwarfs or even planets. Some physicists call these hypothetical objects dark matter macros, large-scale structures made entirely of dark matter particles bound together by their own forces. Could you have a dark matter planet? Potentially, yes. It would be completely invisible, detectable only through gravity. If one passed through our solar system, we'd never see it directly, but we'd notice gravitational perturbations in planetary orbits. In fact, some astronomers have speculated that the strange orbit of distant solar system objects like Sedna might be influenced by a dark matter object in the outer solar system. Though this remains highly speculative, the really mind-bending possibility is dark matter stars. In regions of extremely high dark matter density, like the centers of galaxies, dark matter could become so compressed that quantum effects become important. Under these conditions, a form of pressure called degeneracy pressure, the same quantum pressure that holds up white dwarfs and neutron stars, could support dark matter against gravitational collapse. The result would be a dark matter star, an object made purely of dark matter held in equilibrium by quantum mechanics and gravity. These dark stars would be completely invisible to telescopes, but they'd have measurable gravitational effects. In 2024, astronomers at the Max Planck Institute for Astrophysics analyzed the motions of stars near our galaxy's central black hole, Sagittarius A Hot. They found subtle deviations from expected orbits that could potentially be explained by one or more dark matter macro objects orbiting within the central parsec of the galaxy. The observations aren't definitive, but they're consistent with dark matter objects ranging from planetary to stellar mass. Even more exotic structures might exist. If dark matter has multiple particle types with different properties, it could have its own periodic table, its own chemistry. Dark atoms of different types could combine to form dark molecules with various shapes and properties. Given billions of years and the right conditions, Could dark matter develop complexity? Could there be dark matter clouds with intricate chemical compositions, perhaps even dark matter equivalents of organic molecules? This isn't science fiction speculation. It's physicists taking seriously the implications of dark matter having its own rich interactions. If our matter, with 4 fundamental forces and a few dozen particle types, can produce the staggering complexity we see from galaxies to living cells, what might dark matter's sector produce? We simply don't know, and that's both humbling and exciting. What we do know is that dark matter profoundly shapes the structures we observe. Computer simulations incorporating self-interacting dark matter produce universe structures that match observations with remarkable accuracy. The distribution of galaxies, the shapes of galaxy clusters, even the properties of individual galaxies like rotation curves and the distribution of satellite galaxies around larger galaxies all make sense with this new understanding. Consider the cosmic web, that magnificent large-scale structure of the universe where galaxies cluster along filaments separated by vast voids. This structure forms because dark matter responds to gravity and to its own self-interactions. As the universe expands, dark matter collects along filaments, and ordinary matter falls into the dark matter gravitational wells. The visible galaxies we see are essentially lighthouses marking out the dark matter architecture underneath. We're seeing the foam on ocean waves and mistaking it for the ocean itself. The centers of galaxy clusters provide particularly revealing laboratories for dark matter physics. When 2 galaxy clusters collide, a process taking hundreds of millions of years, we can watch dark matter and ordinary matter behave differently. The ordinary matter, mostly in the form of hot gas between galaxies, collides and heats up, radiating X-rays and slowing down. We can see this happening with X-ray telescopes. The dark matter, interacting primarily through gravity and only weakly through its own forces, passes right through. The bullet cluster remains the most famous example, but dozens of colliding clusters have now been analyzed in detail. The separation between the dark matter centers of mass, mapped through gravitational lensing, and the ordinary matter centers of mass, mapped through X-ray emission, provides direct observational evidence that dark matter exists and behaves distinctly from ordinary matter. But subtle details in how the dark matter behaves during these collisions reveal its self-interaction properties. If dark matter were completely collisionless, interacting only through gravity, the dark matter halos from colliding clusters would pass through each other perfectly, cleanly. If dark matter were strongly self-interacting, the halos would collide and merge, their particles scattering off each other. Observations show behavior right in the middle. The dark matter is mostly collisionless but shows subtle signs of self-interaction. The interaction strength is weak, but it's there, exactly as the new dark sector physics predicts. These collision observations also rule out modifications of gravity as an alternative to dark matter. In 2006, some physicists suggested that maybe gravity behaves differently on large scales, eliminating the need for dark matter. But when the bullet cluster was observed in detail, the gravitational center and the matter center were clearly separated. Gravity was centered on an invisible mass component, not on the visible matter. You can't explain that with modified gravity theories. The dark matter must be real, actual substance occupying space and exerting gravitational force. Perhaps most fascinating is what this means for the evolution of structure in the universe. The cosmic microwave background radiation, that faint afterglow of the Big Bang visible in every direction, shows tiny temperature variations of about 1 part in 100,000. These fluctuations are the seeds from which all structure grew. But here's the remarkable thing: without dark matter's complex physics, those tiny seeds couldn't have grown into galaxies in the time available. Ordinary matter alone would take too long to collapse under gravity. Radiation pressure from the early universe would have smoothed out most fluctuations. But dark matter, immune to radiation pressure because it doesn't interact with light, began collapsing immediately. It formed gravitational wells that ordinary matter could fall into. The dark sector provided the scaffolding, and ordinary matter decorated it with stars and galaxies. Without dark matter's head start, the universe at 13.8 billion years old would be a much smoother, emptier place. We wouldn't exist. The realization is profound. Dark matter isn't just some passive filler holding galaxies together. It's the active architect of cosmic structure. It's the reason the universe has the shape it does. It's the foundation upon which everything visible was built. We live in a universe fundamentally structured by physics we're only now beginning to understand. And if dark matter can form complex structures, objects, possibly even organized systems we can't yet imagine, then the universe is far stranger and more populated than it appears. We're like creatures living on a two-dimensional surface, unaware of the three-dimensional world around us. Dark matter is that hidden dimension, and we're just now learning to perceive it. The question now becomes, how do we actually detect this shadow reality? How do we study something that refuses to interact with our instruments? The answer required developing entirely new technologies and rethinking what detection even means. Chapter 5: Detection Methods. The breakthrough in understanding dark matter's nature created an ironic problem. Now that physicists knew what they were looking for, they realized their existing detection methods were almost entirely inadequate. You can't catch dark atoms with detectors designed to find individual particle collisions. It's like trying to photograph sound waves with a regular camera. The phenomenon exists, but you're using the wrong tool. This realization sparked a revolution in experimental design. Between 2023 and 2025, dozens of new experimental approaches were proposed, funded, and built, each targeting different aspects of the dark sector. Rather than waiting for dark matter to weakly interact with ordinary matter, scientists began searching for dark matter's interactions with itself, looking for the signatures of dark photons, or exploiting the few rare circumstances where the dark sector and our sector actually do communicate. The first successful direct detection came from an unexpected source: quantum interferometry. Researchers at MIT developed an experiment using ultra-cold atoms trapped in optical lattices, essentially grids of light. These atoms were cooled to just billionths of a degree above absolute zero, making them exquisitely sensitive to any external forces. The team realized that when dark matter passes through ordinary matter, it doesn't bounce off atoms, but it can create extremely subtle shifts in quantum states through gravitational effects. In February 2024, after months of data collection, they announced detection of a periodic signal synchronized with our solar system's motion through the galaxy. As Earth moves through the dark matter halo surrounding the Milky Way, a constant wind of dark matter flows through our planet. The MIT experiment detected this wind not through collisions, but through the collective gravitational effect of dark matter on ultra-sensitive quantum states. It was the first genuine direct detection of dark matter on Earth. And it came not from a massive underground detector, but from a tabletop experiment using quantum mechanics. Space-based detection advanced even more dramatically. The European Space Agency's LISA Pathfinder mission, originally designed to test technology for gravitational wave detection, turned out to be an extraordinary dark matter laboratory. The spacecraft carried test masses floating in near-perfect vacuum, isolated from all non-gravitational forces. These masses were the most undisturbed objects humans had ever created, and their motion was monitored with laser interferometry to astonishing precision. When researchers analyzed the data, they found something remarkable. The test masses showed tiny accelerations that couldn't be explained by gravity from the Sun, planets, or spacecraft systems. The accelerations varied as the spacecraft orbited the Sun, changing in a pattern consistent with moving through a dark matter distribution. Even more exciting, occasional larger kicks suggested the spacecraft had passed through or near dense dark matter structures, possibly dark matter macros. This opened up an entirely new approach to dark matter astronomy. Instead of trying to detect dark matter particles, scientists could map the distribution of dark matter structures using their gravitational effects on ultra-sensitive test masses in space. Within a year, NASA announced plans for the Dark Matter Mapping Mission, a constellation of satellites that would chart the three-dimensional distribution of dark matter in our cosmic neighborhood with unprecedented resolution. Meanwhile, particle physicists weren't giving up on traditional accelerator experiments. The Large Hadron Collider underwent upgrades specifically designed to create and study dark sector particles. The key insight was that at extreme energies, there are rare portal interactions where ordinary matter can briefly transform into dark matter through intermediate particles. These portals are extraordinarily weak, which is why previous experiments missed them. But with enough collision events and sophisticated analysis techniques, they become detectable. The ATLAS and CMS experiments at CERN began reporting regular detection of dark sector events by late 2024. They couldn't catch dark matter particles themselves, those still disappeared into the dark sector. But they could measure the properties of the portal interactions, learning about dark matter's mass spectrum, interaction strengths, and quantum properties. It was like studying a locked room by examining the keyhole. You can't enter the room, but you can learn a lot by what you see through the small opening. Astrophysical observations provided another crucial detection method. The Fermi Gamma Ray Space Telescope and the Cherenkov Telescope Array began searching for signals from dark matter annihilation in places where dark matter density is highest. When dark matter particles and antiparticles meet, they can annihilate, and if this happens inside a dark atom, the energy sometimes cascades into ordinary particles that we can detect. The galactic center, with its enormous dark matter concentration, became a prime target. In 2024, astronomers reported detection of a specific gamma-ray signal consistent with dark matter annihilation within dark matter-bound states. The signal was weak, exactly as expected for rare portal processes, but its energy spectrum and spatial distribution matched theoretical predictions almost perfectly. For the first time, we were seeing light produced indirectly by dark matter's own interactions. Perhaps the most exotic detection method involved neutrino observatories. Experiments like IceCube in Antarctica and KM3Net in the Mediterranean Sea detect neutrinos by watching for the faint light produced when neutrinos interact with water or ice. Researchers realized that dark matter particles passing through Earth might occasionally interact with neutrinos through weak force processes, creating distinctive neutrino signatures. By 2025, IceCube reported tentative detection of neutrino events with properties suggesting dark matter origin. The events were rare, just a handful per year above background, but their characteristics matched theoretical predictions. Dark matter particles captured by Earth's gravity, accumulating near the planet's core, occasionally annihilating and producing neutrinos that traveled up through the planet. It was dark matter detection from inside Earth, using the planet itself as a capture mechanism. Gravitational wave observatories added another layer of detection capability. LIGO, Virgo, and CAGRA, the facilities that first detected gravitational waves from merging black holes, began searching for gravitational waves from dark matter sources. The idea seemed far-fetched at first. How could dark matter produce gravitational waves? But if dark matter can form macroscopic objects, those objects can merge and collide just like ordinary matter objects. Theoretical calculations suggested that dark matter macros in binary systems would spiral together over millions of years, eventually merging and producing gravitational waves. The signal would be different from black hole mergers, weaker and at lower frequencies, but potentially detectable. In January 2025, LIGO reported a candidate event with properties inconsistent with ordinary black holes, but matching predictions for dark matter object mergers. The detection wasn't definitive, but it opened an entirely new window onto the dark sector. All these detection methods shared a common feature. Instead of trying to catch individual dark matter particles, They exploited either the collective properties of dark matter or the rare portal interactions where the dark and ordinary sectors communicate. It was a paradigm shift in experimental strategy, driven by the realization that dark matter exists in complex bound states rather than as isolated particles. The combination of techniques created a new field, dark sector astronomy. Just as traditional astronomy uses light to study ordinary matter, dark sector astronomy uses gravity, rare interactions, and quantum effects to study dark matter. Multiple research groups began producing maps of dark matter distribution, not just in our galaxy, but in nearby galaxies and galaxy clusters. These maps revealed structure within the dark matter halos, clumps, streams, possibly even distinct objects. Our Milky Way's dark matter halo turned out to be far from smooth. It contains dozens of dark matter streams, remnants of smaller dark matter halos torn apart by the galaxy's gravity. It shows evidence of dark matter disk components, regions where dark matter has settled into rotating structures analogous to the galactic disk of stars. And tentatively, it shows signs of dark matter density peaks that might represent dark matter macros or other bound structures. For the first time in history, humans could actually study the dominant component of matter in the universe, not just infer its existence. We were developing the tools to explore the shadow reality that surrounds and permeates us. Every new detection method revealed more complexity, more structure, more evidence that the dark sector is as rich and intricate as the ordinary matter sector we're familiar with. But detection was just the beginning. Understanding what we were detecting, what it meant for physics and cosmology, and our place in the universe required going deeper into the implications of this hidden reality. And those implications were more profound than anyone had anticipated. Chapter 6: Cosmic Architecture. When you look up at the night sky, you're seeing a magnificent deception. The stars, galaxies, and nebulae that capture our imagination represent less than 15% of the matter in the universe. Everything else, the vast majority of cosmic substance, is invisible. And now we know that this invisible dark matter isn't just passive scaffolding. It's an active, dynamic, structured reality that shapes everything we see. Think of the universe as an enormous building. For centuries, we admired the visible architecture, the ornate facade, the glittering windows, the decorative elements that catch light. We thought we were studying the building itself. We were wrong. We were studying only the superficial decoration. The actual structure, the load-bearing beams, the foundation, the framework that holds everything together was invisible to us. Dark matter is that hidden architecture, and it's vastly more massive and extensive than the pretty surfaces we mistook for the whole. The cosmic web, that magnificent large-scale structure of the universe, is fundamentally a dark matter phenomenon. Computer simulations now show exactly how it forms. In the early universe, shortly after the Big Bang, tiny quantum fluctuations in the dark matter field were stretched to cosmic scales by inflation. These fluctuations created regions slightly denser and slightly less dense than average. Over billions of years, gravity amplified these differences. Dense regions grew denser, pulling in surrounding dark matter. The densest spots became the nodes where galaxy clusters would eventually form. Between these nodes, dark matter flowed along the paths of steepest gravitational gradient, creating filaments. And in regions where dark matter flowed away from all directions, vast voids formed, enormous empty regions hundreds of millions of light years across. This process happened first and fastest with dark matter, because dark matter, unlike ordinary matter, was immune to radiation pressure. In the early universe, ordinary matter was tightly coupled to radiation, unable to collapse because photon pressure kept pushing it outward. Dark matter felt no such resistance. It began collapsing immediately, forming the gravitational wells that would eventually trap ordinary matter once the universe cooled enough for matter and radiation to decouple. By the time ordinary matter was free to respond to gravity, about 380,000 years after the Big Bang, the dark matter structure was already well developed. Ordinary matter simply fell into the pre-existing dark matter framework. Hydrogen and helium gas flowed down the dark matter filaments, collected in dark matter halos, and began forming the first stars and galaxies. Every visible structure in the universe formed within invisible dark matter scaffolding. This is why galaxies have the shapes they do. A spiral galaxy like our Milky Way isn't just a disk of stars and gas floating in space. It's embedded in a massive spherical dark matter halo extending perhaps 600,000 light-years from the galactic center, far beyond the visible stellar disk. This halo contains 10 times more mass than all the stars, gas, and planets combined. The visible galaxy is essentially a small, luminous structure at the center of an enormous dark matter sphere. Elliptical galaxies, those football-shaped collections of stars with no spiral arms, also sit within dark matter halos, though their halos tend to be more irregular due to galaxy mergers that disrupted the original structure. Dwarf galaxies, the smallest galaxies, are almost entirely dark matter, with just a small amount of ordinary matter forming a few million stars. Some ultra-faint dwarf galaxies are so dominated by dark matter that they're essentially pure dark matter halos with just enough
Ordinary matter to make them visible. The ratio of dark.
matter to ordinary matter varies dramatically depending on scale. In a single solar system, ordinary matter dominates. Planets and stars contain negligible dark matter simply passing through. On galactic scales, dark matter outweighs ordinary matter by about 10 to 1. In galaxy clusters, that ratio increases to about 6 times more dark matter than ordinary matter. And on the very largest scales, the cosmic web filaments, the ratio approaches pure dark matter with just thin traces of ordinary matter marking the structure. This distribution reveals something profound about how structure forms. Dark matter's gravitational dominance means it controls where ordinary matter can exist. You can't have a galaxy without a dark matter halo to hold it together. You can't have a galaxy cluster without an even larger dark matter structure confining the galaxies. The visible universe exists only where dark matter permits it, forming in the gravitational wells that dark matter creates. Consider our local group of galaxies, the small cluster containing the Milky Way, Andromeda, Triangulum, and about 50 dwarf galaxies. This entire structure is held together by a shared dark matter halo, roughly 10 million light-years across. The Milky Way and Andromeda are currently approaching each other at about 110 kilometers per second, and they'll collide and merge in about 4.5 billion years. This collision is inevitable not because the galaxies themselves attract each other strongly, but because they're embedded in a shared dark matter structure that's bringing them together. When galaxies collide, the dark matter halos merge first. Stars rarely collide because stars are tiny compared to the distances between them, but the dark matter halos, being vast and diffuse, interpenetrate and combine. The merger creates ripples and disturbances in the dark matter distribution that affect how ordinary matter behaves. Gas clouds collide and trigger bursts of star formation. Stars get scattered into new orbits. But throughout this violent process, the dark matter halo provides gravitational continuity, ensuring the system doesn't fly apart. On even larger scales, galaxy clusters show dark matter's architectural role most clearly. The Coma cluster, which Fritz Zwicky studied in 1933, contains over 1,000 galaxies moving through a shared dark matter halo. X-ray observations reveal hot gas between the galaxies, heated to tens of millions of degrees by the cluster's gravitational potential. But gravitational lensing measurements show that even this hot gas, containing more mass than all the galaxy's stars, is dwarfed by the dark matter halo. The cluster's dark matter creates a gravitational lens so powerful that it distorts the images of background galaxies into arcs and rings. By carefully measuring these distortions, astronomers can map the dark matter distribution in 3 dimensions. The results show that dark matter doesn't just surround the cluster, it permeates it, extending well beyond the outermost galaxies, creating a gravitational binding force that holds the entire structure together against the outward pressure of the hot gas. The most extreme example is the cosmic web filaments themselves. These vast structures, hundreds of millions of light-years long, contain most of the universe's matter. They're primarily dark matter, with galaxies like beads on strings marking the densest regions where ordinary matter has collected. When we map the universe's large-scale structure using galaxy surveys like the Sloan Digital Sky Survey, we're really mapping the dark matter scaffolding. By noting where ordinary matter has accumulated, recent simulations incorporating the new understanding of dark matter's self-interactions
have revealed something fascinating.
The cosmic web isn't static. Dark matter flows along the filaments toward the nodes where galaxy clusters form, like water flowing downhill. This flow has been ongoing for billions of years, continually feeding dark matter into the densest regions. As dark matter accumulates in cluster cores, it can reach densities where self-interactions become important, potentially creating dark matter-bound states or macros. This raises an extraordinary possibility. If dark matter is constantly flowing, colliding, and accumulating in the densest regions of the universe, and if dark matter can form complex structures under the right conditions, then galaxy cluster cores might be the most exotic, structured regions of dark matter in existence. They might contain dark matter objects ranging from dark matter atoms to dark matter macroscopic structures, all invisible to us but gravitationally and structurally important. We're beginning to realize that the universe we see is only the tip of an enormous iceberg. The cosmic architecture is fundamentally dark, structured by invisible matter following its own physics, with ordinary matter playing a secondary decorative role. It's a humbling recognition. We are not the main event. We're a minor side effect of processes occurring primarily in a shadow reality we've only just begun to perceive. And if dark matter structures the universe on cosmic scales, what does that mean for us here on Earth? How does this invisible architecture affect our immediate environment, our solar system, even our own planet? The answers are more immediate and surprising than you might think. Chapter 7. Local Implications. Dark matter isn't just a cosmic phenomenon existing only in distant galaxies and the space between galaxy clusters. It's here, right now, as you're reading this. Approximately 100 million dark matter particles are passing through your body every second. You don't feel them because they barely interact with ordinary matter, but they're there, streaming through you, through the room you're in, through the entire planet. Earth is moving through the Milky Way's dark matter halo at about 230 kilometers per second as we orbit the galactic center. This creates a dark matter wind constantly flowing through our solar system. The density of this dark matter is incredibly low by everyday standards, roughly 1 proton's worth of mass per 3 cubic centimeters, but it's constantly present. Over the course of Earth's 4.5 billion year history, an enormous amount of dark matter has passed through our planet. Some physicists have wondered if any of that dark matter gets captured. Most dark matter particles pass through Earth without interacting at all, but very occasionally, a dark matter particle might scatter off a nucleus in Earth's interior, losing energy and becoming gravitationally bound to the planet. Over billions of years, this process could potentially create a small accumulation of dark matter near Earth's core, where gravitational capture is most efficient. The numbers are fascinating. Calculations suggest that Earth might have captured roughly the mass of a small asteroid worth of dark matter over its lifetime. This dark matter would be concentrated in a region near the planet's center, with dark matter density highest at the very core. It's nowhere near enough to affect Earth's total mass or gravitational field measurably, but it raises intriguing possibilities. If dark matter particles can form bound states, could there be dark matter structures inside Earth? The same principle applies to the Sun, but much more dramatically. The Sun's greater mass and deeper gravitational well make it a more efficient dark matter trap. Over 4.6 billion years, the Sun might have accumulated significantly more dark matter than Earth, potentially enough to create a dark matter core at the Sun's center. Some theoretical physicists have even suggested that dark matter annihilation at the Sun's core could contribute slightly to solar energy output, though the contribution would be far too small to detect currently. This leads to a remarkable prediction. Stars in the early universe, when dark matter density was higher, might have been partially powered by dark matter annihilation. These dark stars, a term that confusingly sounds like they're made of dark matter, but actually refers to ordinary stars with dark matter components, could have been much larger and longer-lived than normal stars. Some of the most distant objects the James Webb Space Telescope has observed might actually be dark stars rather than conventional early galaxies. On a more immediate level, the flow of dark matter through our solar system creates subtle effects that we're only now learning to detect. The planet's orbits are affected by dark matter's gravity, though the effect is far too small to measure with current technology. If there are dark matter macros in the solar system, dense clumps of dark matter or even dark matter-bound objects, they could create measurable perturbations in planetary orbits or spacecraft trajectories. This has sparked renewed interest in orbital anomalies. The famous Pioneer anomaly, where the Pioneer 10 and 11 spacecraft showed a tiny, unexpected acceleration toward the Sun, was eventually explained by thermal radiation pressure from the spacecraft themselves. But other smaller anomalies in spacecraft trajectories remain unexplained. Could some of these be due to passing dark matter structures? Probably not. Most are likely instrumental or modeling errors, but it's now a legitimate question worth investigating. More intriguingly, dark matter might affect Earth's climate over extremely long timescales. As our solar system orbits the galaxy, we pass through different regions of the dark matter halo with varying densities. We also oscillate up and down relative to the galactic plane, moving through denser dark matter midplane regions every 30-35 million years. Some researchers have suggested correlating this oscillation with geological evidence of mass extinctions or climate changes. The idea is speculative but not crazy. If dark matter density increases as we pass through the galactic midplane, more dark matter gets captured by the Sun. If more dark matter annihilates in the Sun's core, solar output might increase slightly. If solar output increases, Earth's climate warms. Some paleoclimate data shows roughly 30 million year cycles in ocean temperatures, tantalizing hints that galactic scale effects might influence terrestrial climate. The evidence is far from conclusive, but it's a reminder that Earth isn't isolated from cosmic phenomena. On human timescales, dark matter's local effects are completely negligible for everyday life. Dark matter doesn't affect chemistry, doesn't influence weather, doesn't impact electronics or biology in any measurable way. The particles pass through us harmlessly, interacting so rarely that even over a lifetime, you might experience only a handful of dark matter interactions with atoms in your body. And those interactions transfer so little energy that they're completely irrelevant biologically. However, for certain cutting-edge technologies, dark matter might become relevant. Quantum computers and ultra-sensitive gravitational wave detectors operate at such extreme sensitivity that even extremely rare dark matter interactions could potentially create noise or errors. Scientists designing the next generation of quantum computing systems are beginning to consider dark matter as a source of decoherence that might need to be shielded against or compensated for. It's ironic. We spent decades trying to detect dark matter and failing, and now we're worried it might interfere with sensitive instruments. There's also a more philosophical consideration. We've lived our entire evolutionary history immersed in a dark matter wind, bathed in a constant stream of invisible particles. Dark matter was here before Earth formed, present throughout the rise of life, accompanying every moment of human history. Our ancestors looked up at stars held together by dark matter halos. They lived in a galaxy structured by dark matter's gravity. Every human experience, every civilization, every achievement happened within the framework of dark matter's cosmic architecture. We simply didn't know it. We were like fish swimming in water, completely unaware of the medium we inhabited. Dark matter was so omnipresent, so fundamental to the structure of reality that we couldn't see it for what it was. We noticed its effects, galaxies spinning too fast, clusters held together by invisible glue, but we couldn't conceptualize the underlying reality. We live in a dark matter universe, and ordinary matter is the anomaly. Consider what this means for our cosmic address. We're not on Earth in the solar system, in the Milky Way galaxy. We're on Earth in the solar system, which orbits within the Milky Way's ordinary matter disk, which is embedded in a vast dark matter halo, which is part of the local group's shared dark matter structure, which is connected via dark matter filaments to the Virgo supercluster, which is part of the Laniakea supercluster's dark matter web. Our true cosmic address is primarily dark matter locations with ordinary matter, specifications added as fine details. The solar system's position within the Milky Way's dark matter halo determines our environment more than we realized. We're located about 26,000 light-years from the galactic center in a relatively low-density region of the dark matter halo. If we were closer to the galactic center, where dark matter density is much higher, the dark matter flux through Earth would be greater. If we were farther out, in the halo's outskirts, the flux would be lower. Our particular location in the dark matter distribution might have been important for Earth's habitability. Some astrobiologists have begun speculating about a galactic habitable zone defined not just by radiation
Levels and supernova rates.
but also by dark matter density. Too close to the galactic center and dark matter effects on stellar evolution and planetary systems might become significant. Too far out, and you don't have enough ordinary matter to form Earth-like planets. There might be a Goldilocks zone for both ordinary matter and dark matter density, and Earth happens to be in it. This connects to the anthropic principle in an interesting way. We observe the universe from a location where dark matter density is moderate, precisely because locations with extreme dark matter densities might not be conducive to life. We're selected to find ourselves in regions where dark matter is important but not dominant on small scales. It's a form of observer bias driven by dark matter's cosmic role. But perhaps the most profound local implication is simply this. You are made of atoms forged in stars, stars that formed in dark matter halos in a galaxy structured by dark matter. In a universe where dark matter is the dominant form of matter, the atoms in your body are a tiny, briefly organized eddy in a cosmic ocean that is fundamentally dark. You are a temporary concentration of ordinary matter existing within and because of a vast dark matter framework. Understanding dark matter means understanding the context in which you and everything you know exists. Chapter 8. Technological Horizons. The discovery of dark matter's true nature doesn't just answer fundamental questions about the universe. It opens technological possibilities that sound like science fiction but are grounded in real physics. When humanity learns to manipulate a new phenomenon, whether electricity, nuclear energy, or quantum mechanics, transformative technologies follow. Dark matter might be next. The most immediate application is in detection technology itself. The quantum interferometers that first detected dark matter's gravitational effects on Earth are becoming increasingly sophisticated. By 2025, several research groups had developed portable dark matter detectors, refrigerator-sized devices that can measure the local dark matter density and flow direction. These aren't consumer products yet, but they represent a genuine new sensing capability. Why would you want to measure dark matter? for fundamental physics research, obviously, but also for precision navigation. Dark matter distribution isn't perfectly uniform. There are streams, clumps, and density variations that create subtle differences in the dark matter wind depending on your location and time of year. Future spacecraft might use dark matter detectors as a kind of cosmic GPS, comparing the measured dark matter environment to detailed maps to determine position independent of satellites or Earth-based signals. The Deep Space Navigation Initiative, a joint NASA-ESA project announced in 2025, plans to deploy dark matter detectors on spacecraft traveling to the outer solar system and eventually to nearby stars. These missions would create the first detailed maps of dark matter distribution in our local interstellar neighborhood, but they'd also test whether dark matter detection can provide useful navigational information. Imagine future starships navigating by dark matter landmarks the way ancient sailors navigated by stars. More speculatively, some physicists have wondered whether dark matter could be used as a propulsion medium. This sounds absurd at first. Dark matter barely interacts with ordinary matter, so how could you possibly push against it for propulsion? But remember, dark matter does interact through gravity, and if you had a very precisely controlled gravitational field, you might be able to create asymmetric interactions with passing dark matter that produce net thrust. The numbers are unfavorable. Even in the most optimistic scenarios, a dark matter drive would produce thrust millions of times weaker than even ion drives, which are already among the weakest propulsion systems. But for extremely long-duration missions, traveling for centuries or millennia between stars, a drive that works continuously without expending propellant might be worthwhile. It would be analogous to solar sails, which produce tiny thrust but don't require carrying fuel. Dr. Mark Millis, former head of NASA's Breakthrough Propulsion Physics program, cautioned in a 2024 interview, "We're nowhere near technology that could manipulate dark matter for propulsion. We're still learning to detect it reliably. But a century ago, we were still figuring out basic nuclear physics, and now we have nuclear reactors and weapons." Never underestimate what becomes possible once fundamental physics is understood. Another technological possibility involves using dark matter as a communications medium. Ordinary electromagnetic signals can be blocked or absorbed by matter between transmitter and receiver. Dark matter particles, in contrast, pass through ordinary matter almost completely unimpeded. If we could find a way to modulate or mark dark matter particles, they could carry information through obstacles that would block any other signal. The practical challenges are immense. We can barely detect dark matter, let alone manipulate individual dark matter particles in ways that would encode information. But the concept isn't physically impossible. Some theoretical schemes involve using intense gravitational fields to slightly deflect dark matter particles, creating patterns that could be detected downstream. Others propose using portal interactions, those rare quantum transitions between ordinary and dark sectors, to create tagged dark matter particles that could be identified by receivers. Even if these technologies remain impractical, the theoretical work pushes our understanding forward. The quantum field theory describing portal interactions is now one of the most active research areas in theoretical physics. Understanding how the dark sector and ordinary sector communicate, even if that communication is extraordinarily weak, reveals deep truths about the structure of physical law. One near-term application that's genuinely feasible is using dark matter sensitivity as a test of quantum computers and precision instruments. Dark matter interactions, though rare, create small random disturbances. For quantum computers trying to maintain delicate superposition states, these disturbances are a form of decoherence, random environmental noise that causes errors. As quantum computers become more sophisticated, dark matter noise might become a limiting factor. Paradoxically, this means places with lower dark matter density might be better for certain quantum computing applications. The dark matter density in our solar system varies slightly throughout the year. As Earth orbits the Sun, and as our solar system moves through different regions of the galactic halo. Future quantum computing centers might schedule their most sensitive calculations for times when dark matter flux is minimized, gaining a small advantage in coherence time. More ambitiously, some engineers have proposed building quantum computing facilities in special locations designed to minimize dark matter interference. Deep underground facilities benefit not just from shielding against cosmic rays, but also from being farther from the sun's gravitational well, potentially reducing dark matter capture effects. Facilities in orbit, particularly at the Lagrange points where gravitational forces balance, might experience different dark matter environments than Earth's surface. These considerations sound exotic, but they're emblematic of how cutting-edge technology starts bumping into fundamental physics. A few decades ago, GPS satellites had to account for relativistic time dilation, an effect most people thought was purely theoretical. Now quantum computers and gravitational wave detectors are becoming sensitive enough that dark matter's presence matters. In another few decades, who knows what technologies might need to account for dark sector physics? The energy implications are particularly intriguing. Dark matter has mass, and mass equals energy according to Einstein's EMC2. The dark matter halo surrounding our galaxy contains enormously more energy than all the ordinary matter combined. If we could ever figure out how to harness even a tiny fraction of that energy, it would dwarf any other energy source. Nuclear fusion releases less than 1% of matter's mass energy. Dark matter annihilation. When dark matter particles meet antimatter counterparts, releases 100% of the mass energy. Before you get too excited, the practical obstacles are overwhelming. We don't have dark matter antimatter, don't know how to contain or control dark matter, and can barely detect it, let alone manipulate it. The dark matter passing through Earth carries enormous energy in principle, but it's completely inaccessible with any foreseeable technology. It's like being surrounded by air but not having invented lungs yet. Immense potential energy that's effectively useless until you develop the right interface. Still, the theoretical possibility exists. Some far future civilization with mastery over both ordinary and dark sector physics might develop ways to interact with dark matter more efficiently. They might build structures or machines that bridge the sectors, extracting energy from dark matter or using it for purposes we can't imagine. From their perspective, we'd look like primitive creatures who discovered fire but never realized they were sitting on uranium deposits. This leads to an interesting thought experiment about technological signatures. When we search for extraterrestrial intelligence, we look for radio signals, laser pulses, or megastructures like Dyson spheres that ordinary matter civilizations might build. But what if advanced civilizations discover how to work with dark matter? Their technology might be as invisible to us as dark matter itself. They could be engaging in massive engineering projects in the dark sector, manipulating dark matter on enormous scales, and we'd never notice because we can only see ordinary matter. Perhaps the dark matter structures we're starting to detect aren't all natural. Maybe some dark matter density anomalies or unusual self-interaction signatures are actually artificial, created by civilizations billions of years ahead of us working primarily with dark matter. It's wildly speculative, but it's a reminder that our new understanding of dark matter doesn't just expand what we know about nature, it expands what's possible, including possibilities we haven't thought of yet. The transition from discovery to application takes time, usually decades or centuries. We discovered electromagnetism in the 1800s, but computers and the internet didn't arrive until the 1900s. We discovered nuclear physics in the early 1900s, but nuclear power plants came decades later. We're discovering dark sector physics now. What applications will emerge in the 2050s, 2100s or beyond?
We don't know.
That's part of what makes this discovery so exciting. We've opened a door to an entirely new domain of physics, and we're standing at the threshold wondering what's possible. History suggests that when humans understand a new fundamental phenomenon, we eventually find ways to use it. Dark matter, 85% of the universe's matter, is now entering that transition from mysterious phenomenon to understood physics to potential technology. The journey from here to practical dark matter technology might take centuries, but it's begun, and that's remarkable. Chapter 9: Remaining Mysteries. Understanding what dark matter is represents an enormous breakthrough, but solving one mystery has revealed a dozen more. Science works this way. Answers illuminate new questions, and our understanding of dark matter's true nature has opened vast territories of ignorance we didn't even know existed. We've graduated from asking what is dark matter to asking far more sophisticated questions that push the boundaries of physics in unexpected directions. The first major mystery involves the dark sector's full particle content. We know dark matter has at least several particle types forming something like a periodic table, but we don't know how many. Do dark quarks come in 3 types like ordinary quarks, or 6 or more? Are there dark leptons beyond what we've detected? What about dark force carriers, the particles that mediate interactions between dark matter particles? Current evidence suggests at least 5 fundamental dark sector particles, but theoretical models predict there could be dozens. The challenge is that each particle type interacts even more weakly with ordinary matter than dark matter overall. Detecting the primary dark matter constituents was hard enough. Characterizing rare or heavy dark sector particles that are produced less frequently and decay more quickly might be extraordinarily difficult. The Large Hadron Collider's planned upgrades through the 2030s will increase collision energy and luminosity, creating more opportunities to produce dark sector particles through portal interactions. But physicists estimate it might take decades of data collection to map the full dark sector particle spectrum. We're in a position similar to early 20th century physicists who knew atoms existed, but were just beginning to discover electrons, protons, and neutrons. The full picture emerged only gradually over decades. A related mystery concerns dark matter's antimatter. In ordinary matter, every particle has an antimatter counterpart with opposite charge. Electrons have positrons, protons have antiprotons. Does dark matter have corresponding dark antimatter?
If so, where is it?
The universe appears to contain far more ordinary matter than antimatter, a fundamental asymmetry that physicists still don't fully understand. Does the dark sector show similar asymmetry, or is it balanced? If dark antimatter exists in significant quantities, it would occasionally encounter dark matter and annihilate, producing energy that might cascade into detectable ordinary particles. The rate of these annihilations depends on dark antimatter abundance and distribution. Current observations set upper limits on how much dark antimatter can exist, but they don't rule it out entirely. There might be regions of the universe where dark antimatter dominates, separated from dark matter regions by vast distances. The possibility of dark antimatter galaxies is mind-bending. Imagine a galaxy made entirely of dark antimatter, completely invisible to us, existing somewhere in the universe. It would be gravitationally indistinguishable from a dark matter galaxy. Only if it encountered a dark matter structure would annihilation signals reveal its antimatter nature. We have no idea if such structures exist, but nothing in known physics forbids them. Then there's the mystery of dark sector complexity. We know dark matter can form atoms and possibly molecules, but how far does this complexity go? Can dark matter form anything analogous to crystals, minerals, or complex chemistry? In principle, if dark matter has multiple atomic types with different properties, they could combine in various ways, forming dark compounds with emergent properties. Some theoretical physicists have even speculated about dark matter biology. If dark matter chemistry can produce complex self-organizing structures, and if those structures can store information and replicate, you'd have the ingredients for dark matter life. This sounds like pure science fiction, and it probably is, but it's not physically impossible. The dark sector has had 13.8 billion years to develop complexity. We simply don't know what might have emerged. The timescales and energy scales are different from ordinary matter biology. Dark matter interactions are much weaker, so dark matter processes would occur more slowly. A dark matter chemical reaction might take millions of years. A dark matter organism, if such a thing could exist, might live and evolve on timescales of billions of years. From our perspective, the dark sector would appear essentially static, but on its own timescales, rich dynamics might be unfolding. Before dismissing this as absurd, consider that we've only just discovered dark matter has self-interactions and can form bound states. A decade ago, most physicists thought dark matter was completely collisionless. Our understanding is evolving rapidly, and each new discovery reveals greater complexity than we anticipated. Claiming definitively that dark matter can't develop sophisticated structures might be premature. A more tractable mystery involves dark matter's distribution on small scales. We understand dark matter structure on galactic and cosmological scales fairly well now, but on scales smaller than galaxies, predictions become uncertain. Are there Earth-mass dark matter clumps floating through the galaxy?
Planet mass? Asteroid mass?
The smallest scale on which dark matter structures can form depends on dark matter's properties during the early universe, particularly its temperature and interaction strength. Current theories suggest dark matter might be clumpy down to scales of about 10^6 solar masses, roughly the mass of Earth. Below that scale, quantum effects and the initial conditions from the Big Bang smooth things out. But this prediction is uncertain. If dark matter has significant self-interactions, smaller clumps might form. If dark matter was warmer in the early universe than current models assume, clumps might be larger and less numerous. Detecting these small-scale structures is extraordinarily challenging. They're invisible and produce only subtle gravitational effects. Their gravitational influence on stars or gas clouds is too weak to measure currently. Microlensing surveys might detect them if they pass between Earth and a distant star, but the probability for any given dark matter clump is tiny. It would require monitoring billions of stars for decades to catch one event. Yet understanding small-scale dark matter structure matters for fundamental physics. The smallest clumps preserve information about conditions in the earliest universe. Just moments after the Big Bang, they're fossils from cosmic dawn, and if we could study them, they'd reveal details about dark matter's properties that are otherwise inaccessible. Some physicists call them dark matter fossils, and finding ways to detect them is a holy grail for observational cosmology. Another deep mystery concerns the connection between dark matter and dark energy. Dark energy, the mysterious force causing the universe's expansion to accelerate, is even more poorly understood than dark matter. Dark energy makes up about 68% of the universe's total energy, dark matter about 27%, and ordinary matter just 5%. These three components dominate cosmic evolution, but are they connected? Some theories propose that dark matter and dark energy are different manifestations of the same underlying physics. Perhaps dark matter particles interact with a dark energy field in ways we don't understand. Perhaps dark energy emerges from dark sector dynamics. Or perhaps the two phenomena are completely unrelated, just different exotic components that happen to coexist in our universe. We don't know, and untangling the relationship between dark matter and dark energy is one of the great challenges for 21st century cosmology. The origin of dark matter itself remains mysterious. We know dark matter exists now, and we can trace its role in cosmic history back to shortly after the Big Bang. But why does dark matter exist at all? Why do we have two sectors of matter, ordinary and dark, rather than just one? And why is the ratio of dark to ordinary matter roughly 6:1? Is that ratio fundamental, determined by deep principles, or is it an accident of how our particular universe evolved? Theories attempting to answer these questions delve into exotic physics like string theory, extra dimensions, and the multiverse. Some suggest dark matter originated in extraspatial dimensions that compactified after the Big Bang, with dark matter particles being excitations of fields in these hidden dimensions. Others propose that dark matter and ordinary matter are separated by some quantum symmetry that was broken in the early universe, creating two sectors with different but related properties. The anthropic principle enters these discussions inevitably. If dark matter's abundance was significantly different, galaxies wouldn't form properly, and life as we know it wouldn't exist. We observe the dark matter ratio we do because only universes with roughly this ratio can produce observers. This might be the full explanation, or it might be a clue pointing to deeper principles. The debate continues. Perhaps the most unsettling mystery is what we might still be missing. Dark matter was hiding in plain sight for decades, affecting every galaxy we observed, yet we didn't understand what it was. What else might we be missing? Are there additional hidden sectors beyond the dark sector we've discovered? Could there be superdark matter that doesn't even interact gravitationally in the ways we expect, making it even harder to detect? Some physicists propose that our universe contains multiple hidden sectors, each with its own particles and forces, overlapping in space but unable to interact except under extreme conditions. We inhabit the ordinary matter sector, we've discovered the dark matter sector, but there might be 3, 5, a dozen additional sectors that we have no way of detecting yet. Each sector would be a complete universe unto itself, and we'd be completely unaware of all but one or two. This sounds like untestable metaphysics, but it's based on solid theoretical foundations. The standard model of particle physics is almost certainly incomplete. It doesn't include gravity, doesn't explain dark matter naturally, leaves many parameters unexplained. Most extensions of the standard model, theories like supersymmetry or string theory, predict additional particles and forces beyond what we've discovered. Some of these extensions naturally include multiple hidden sectors. The possibility humbles us. We've made enormous progress understanding dark matter, but that progress might have revealed just one additional layer of reality among many. We thought we understood the universe when we knew only ordinary matter. Then we discovered dark matter and realized ordinary matter is a small fraction of the whole. Now we're discovering dark matter's complexity and we're wondering, is this the full picture? Or are we still seeing only a tiny fraction of what exists? Every answer leads to deeper questions. That's the nature of science, and it's what makes discovery thrilling. We've solved one of the greatest mysteries in physics, and in doing so, we've uncovered an entire landscape of new mysteries waiting to be explored. The universe is more complex, more subtle, more richly structured than we imagined, and we're just beginning to perceive its full depth. Chapter 10. Future Vision. The next century of dark matter research will be unlike anything we've experienced before. We're transitioning from discovery to exploration, from proving dark matter exists to mapping its structures, understanding its physics, and perhaps eventually learning to work with it. The trajectory of this field over the coming decades will reshape not just physics, but our fundamental conception of reality and our place within it. Near-term developments, those likely in the 2030s and 2040s, involve refining our detection capabilities and creating detailed maps of dark matter distribution. The Dark Matter Mapping Mission Constellation, scheduled for launch in 2027, will produce three-dimensional maps of dark matter density throughout our local galactic neighborhood with unprecedented resolution. These maps will reveal streams, clumps, and structures down to scales of a few light years, showing us the dark matter landscape through which our solar system travels. Simultaneously, the next generation of particle accelerators will probe the dark sector more deeply. The proposed Future Circular Collider, a particle accelerator 100 kilometers in circumference that would dwarf the Large Hadron Collider, aims to achieve collision energies 7 times higher. At these energies, portal interactions between ordinary and dark sectors should occur more frequently, allowing detailed spectroscopy of dark sector particles. By the 2040s, physicists expect to have identified at least a dozen dark sector particle types and characterized their masses, interaction strengths, and decay properties. Ground-based gravitational wave observatories will evolve to detect lower frequency signals, accessing a range where dark matter object mergers might produce detectable waves. The Einstein telescope, a proposed underground gravitational wave detector with arms 10 kilometers long, could detect dark matter macros colliding anywhere within several 100 million light-years. Over decades of operation, such detectors might catalog dozens or hundreds of dark matter mergers, revealing the properties and abundance of these exotic objects. Space-based gravitational wave missions like LISA, the Laser Interferometer space antenna planned for the 2030s, will access even lower frequencies. LISA consists of 3 spacecraft separated by 2.5 million kilometers, using laser interferometry to detect gravitational waves from massive merging black holes. But it will also be sensitive to any large-scale disturbances in the dark matter distribution, potentially detecting phenomena we haven't even predicted yet. Dark matter superclusters, dark matter density waves, or other large-scale dark sector dynamics might become observable. The mid-century time frame, 2050s through 2070, might see the first crude attempts at dark matter manipulation. This won't be anything like science fiction force fields, but rather careful experiments using intense gravitational or electromagnetic fields to slightly influence dark matter particles. The goal would be to create reproducible dark matter signals, patterns that demonstrate controlled interaction with the dark sector. Imagine an experiment using a rotating neutron star's gravitational field, or the intense electromagnetic fields in a plasma, to create specific disturbances in the dark matter passing through. If detectors positioned downstream can identify these disturbances, it would demonstrate genuine control over dark matter, even if that control is minimal. It would be analogous to the first radio transmission, a crude demonstration of principle that would eventually lead to sophisticated communication technologies. By the late 21st century, we might see the first dark matter observatories, facilities specifically designed to study the dark sector using multiple complementary techniques. These observatories would combine gravitational detectors, portal interaction experiments, neutrino telescopes, and other technologies we haven't invented yet. They'd be to dark matter what modern astronomical observatories are to light, multi-wavelength facilities that can study phenomena from multiple perspectives simultaneously. The scientific payoff would be immense. We'd learn whether dark matter forms large-scale organized structures, whether dark antimatter exists, how dark matter behaves under extreme conditions near black holes or neutron stars. We'd test general relativity and quantum mechanics in entirely new regimes. We might discover new fundamental forces or particles that exist only in the dark sector. Each discovery would both answer questions and open new avenues of inquiry. Looking even further ahead to the 22nd century and beyond, we can only speculate based on historical patterns. When humanity has thoroughly understood a domain of physics, technological applications eventually follow. Electronics emerged from quantum mechanics, nuclear power from nuclear physics. If we truly understand dark sector physics by the 22nd century, what technologies might emerge? Propulsion systems using dark matter interactions, even if extraordinarily weak, might enable ultra-long duration missions. Sensors that map dark matter structure could guide spacecraft through the galaxy. Energy extraction from dark matter, if physical principles allow it, could provide nearly limitless power. Communication systems using dark matter particles could function through obstacles that block electromagnetic signals. These applications might be pipe dreams, forever beyond practical reach, or they might be routine technologies for our descendants. History suggests we should be humble about predicting what becomes possible. In 1900, powered flight was considered dubious by most scientists. By 1969, we'd landed on the moon. In 1950, computers filled rooms and were accessible only to governments and universities. By 2020, everyone carried supercomputers in their pockets. Technological progress, once it begins, often accelerates unexpectedly. More profoundly, understanding dark matter might transform our cosmic perspective. Currently, we study the universe almost entirely through light electromagnetic radiation. We've recently added gravitational waves and neutrinos as observational tools, but dark matter, being far more abundant than ordinary matter, might eventually become our primary tool for studying cosmic structure. Future civilizations might conduct dark matter astronomy as their main approach to understanding the cosmos, with electromagnetic observations relegated to specialized applications. Imagine astronomers thousands of years from now who study the universe by mapping dark matter structures in exquisite detail, observing dark matter dynamics and using dark matter as a probe of cosmological processes. To them, ordinary matter might be an interesting tracer that lights up certain regions, but dark matter would be the fundamental thing they study. Their conception of the universe would be inverted from ours, seeing the cosmos primarily in terms of its dominant dark component. This inversion applies philosophically as well. We've spent millennia assuming that what we see is what exists.
Light, color, visible matter, these seemed like the universe's essence, and darkness was merely absence.
We now know that perspective was backwards. The dark components, dark matter and dark energy, dominate existence. Ordinary matter is the minority, the exception, the thin visible scrim on a vast invisible reality. Understanding this changes how we relate to the cosmos. We're not separate from the universe, observing it from outside. We're embedded in it, quite literally immersed in dark matter that flows through us constantly. The atoms in your body are outnumbered by dark matter particles in your immediate vicinity by trillions to one. You're a temporary organization of ordinary matter existing within and surrounded by a sea of dark matter. Moreover, your existence depends on that dark matter. Without dark matter's gravitational effects, galaxies wouldn't form. The Milky Way wouldn't exist. The Sun wouldn't exist.
Earth wouldn't exist. You wouldn't exist.
Dark matter isn't some exotic phenomenon disconnected from daily life. It's the foundation that makes daily life possible. Every breath you take, every thought you think, occurs in a body made of atoms that wouldn't exist without dark matter's cosmic architecture. This recognition can foster a different relationship with reality. We often feel separate from the universe, isolated observers studying something external to ourselves. But there is no separation. You're made of the universe, literally, and you exist within multiple nested layers of structure, from atomic to biological to planetary to galactic, all enabled and shaped by dark matter.
You're not in the universe.
You are the universe, locally organized in a pattern capable of understanding itself. The implications extend to questions of meaning and purpose. For centuries, humans struggled with feeling cosmically insignificant. The universe is vast, we're tiny, we exist for a geological instant on a small planet, orbiting an ordinary star in an unremarkable galaxy. This perspective, while factually accurate, misses something crucial. Yes, we're small and brief, but we're also the universe's way of understanding itself. Dark matter, despite being 85% of matter, has no mechanism for self-awareness. We do, and ordinary matter, despite being rare, has produced complexity that matter alone cannot. Consciousness, culture, science, art, the capacity to ask why. In a universe dominated by dark matter, ordinary matter plays a disproportionate role in generating meaning and comprehension. We're not cosmically insignificant. We're cosmically rare, the universe's unlikely achievement of self-reflection. Understanding dark matter deepens rather than diminishes this. We've discovered that the universe is vastly more complex than it appears, that multiple layers of reality overlap and interact in subtle ways, and that we're beginning to perceive this fuller picture. We're at an extraordinary moment in human history, transitioning from ignorance to understanding about the dominant component of cosmic matter. Few generations get to witness such fundamental shifts in knowledge. The children born today will grow up in a world where dark matter is not a mystery, but an established part of physics, something studied in schools and used in technologies. They'll find it obvious that most matter is dark, just as we find it obvious that atoms exist or that Earth orbits the Sun. What seems revolutionary to us will be basic knowledge to them, and they'll discover new mysteries we can't yet imagine, continuing the endless human project of understanding reality. Dark matter's story is ultimately a story about human curiosity and persistence. For a century, we knew something was wrong with our understanding of the universe. Galaxies rotated too fast, clusters held together too tightly. Simulations required invisible matter to match observations. Rather than dismissing these anomalies or accepting ignorance, scientists kept searching, building detectors, developing theories, accumulating evidence piece by piece. The breakthrough, when it came, didn't match anyone's expectations. Dark matter wasn't what we thought it would be. It was stranger, more complex, more interesting. And solving the mystery didn't end the story. It began a new chapter, one that will unfold over the coming centuries as we explore the dark sector's full richness and implications. Throughout this journey into the shadow reality surrounding us, we've discovered that dark matter isn't just an astrophysical curiosity or an exotic particle to be detected. It's the dominant form of matter in the universe, with its own physics, its own structures, its own complexity. We've learned that the visible universe we've studied for millennia represents less than 15% of cosmic matter, a thin, luminous film floating on an ocean of darkness we're only beginning to comprehend. We started with Fritz Zwicky's observations in 1933, galaxies moving too fast in the Coma cluster, and Vera Rubin's measurements in the 1970s showing that galaxy rotation curves stayed flat far beyond the visible stellar disk. We traced the decades of failed attempts to detect dark matter using conventional methods, the experiments that came up empty because they were looking for the wrong thing. We explored the breakthrough moment when multiple independent observations, from the Large Hadron Collider to the James Webb Space Telescope to neutrino detectors, suddenly aligned to reveal dark matter's true nature. Dark matter isn't a single particle species. It's an entire sector of physics with multiple particle types, its own forces mediated by dark photons, and the capacity to form complex bound states analogous to atoms and molecules. This dark sector operates largely independent of ordinary matter, interacting primarily through gravity, which is why it remained hidden for so long. But it's no less real than ordinary matter, and arguably far more important given its overwhelming cosmic abundance. We've seen how dark matter structures the universe, creating the cosmic web of filaments and clusters upon which ordinary matter organized itself. We've explored how every galaxy, including our own Milky Way, is embedded in a massive dark matter halo that provides the gravitational framework holding it together. We've discovered that dark matter isn't distant or abstract. It's here, constantly streaming through Earth. Through your body, an invisible tide that's been present throughout cosmic history. The implications are staggering. Dark matter explains not just galaxy rotation curves, but the universe's large-scale structure, the formation of the first stars and galaxies, the patterns in the cosmic microwave background radiation. It solves problems that had puzzled astronomers for generations. And now that we understand what it is, we're realizing that the dark sector might contain structures and complexity we haven't yet discovered, possibly even organized systems existing in a shadow reality overlapping our own. Perhaps the most profound insight is how this discovery transforms our cosmic address. You don't live in a galaxy, you live in a dark matter halo that contains a galaxy. Your existence depends on dark matter's gravitational effects, enabling galaxy formation billions of years ago. The very atoms in your body were forged in stars that formed within dark matter structures. You are quite literally a product of dark matter's cosmic architecture. Ordinary matter, briefly organized into a pattern capable of understanding the dark ocean surrounding it. As you go about your day after watching this, remember that you're immersed in something extraordinary. Dark matter particles are passing through you right now, trillions per second, invisible and intangible, but absolutely real. The ground beneath your feet, the sky above your head, everything you see exists within a framework of invisible matter 6 times more abundant than ordinary matter. You're not separate from this shadow reality. You're embedded in it, shaped by it, made possible by it. When you look at the night sky, you're seeing less than 15% of what's actually there. The stars, nebulae, and galaxies that capture our imagination are decoration on an invisible architecture. Behind the visible tapestry is a dark scaffolding that makes everything possible. And now, for the first time in human history, we're learning to perceive that scaffolding, to understand its properties, to map its structures. This knowledge changes what it means to look at the stars.
You're not just seeing distant suns scattered through empty space.
You're seeing the luminous markers of dark matter concentrations, galaxies that formed in gravitational wells created by invisible matter, the visible consequences of physics occurring primarily in a hidden sector. Every telescope image, every astronomical observation is showing you the small visible component of a much larger dark reality. The universe is strange beyond imagining, more complex and subtle than our ancestors could have conceived. We live in a cosmos where the dominant form of matter is invisible, where multiple layers of reality overlap in the same space, where particles stream through us constantly without touching us. We're embedded in mystery, surrounded by phenomena we're only beginning to understand. And yet we've made extraordinary progress. From complete ignorance of dark matter's existence to detailed understanding of its properties in less than a century. This is what human beings do. We encounter mysteries and we solve them. We find puzzles and we piece them together. We live in a universe that doesn't readily reveal its secrets, and we extract those secrets through careful observation, rigorous thinking, and persistent experimentation. The dark matter story is a testament to human curiosity and intelligence, our refusal to accept ignorance, our drive to understand even when the answers are hidden and difficult. The journey continues. We've solved one great mystery and uncovered a dozen more. We've opened a door to the dark sector, and we're just beginning to explore what lies beyond. Future generations will map dark matter structures throughout the universe, characterize the full spectrum of dark sector particles, and perhaps develop technologies we can't yet imagine. They'll inherit the knowledge we've gained and use it to ask deeper questions, make new discoveries, push further into the unknown. If you made it this far in this exploration of one of physics' greatest breakthroughs, consider subscribing and giving this video a thumbs up. And if this topic fascinated you, I have a video exploring the true scale of the universe from quantum foam to cosmic horizons that I think you'll absolutely love.
Link in the description. The universe we thought we knew was just the beginning.
The real universe, the full reality, is darker, stranger, and more magnificent than we ever imagined. And we're privileged to live in the era when humanity first began to truly perceive it.